Hi everyone. So in this video, we're going to talk about basis and dimensions of a vector space. So last time we talked about how to decide whether a set of vectors are dependent on one another. And this we call linear dependence or linear independence. So in this case, what we're going to try to do is try to see when we can kind of have a maximum amount of vectors that are linearly independent of one another. Like what this kind of looks like. In essence, the idea here is that we're trying to be able to get any vector in our vector space from some set of vectors. So this is the main idea. So what we're going to do is first we're going to define that idea of how do we get any vector from some set of vectors. Well, so if I give you a set of vectors, what does that define? What does that give me as a vector space? And this is what we define as a span. So the span of a set of vectors. So here is a set of vectors. Span is a set of all vectors that can be linearly written as a linear combination of some of these sets of this set. So in other words, the span here is equal to the set of vectors. So Y in our vector space, such that, so here we have it bolded, Y is equal to some linear combination. We have M of these vectors, right? So the set is size M, so I to M, and we're going to set lambda I, xi. And here we're just going to make sure that lambda I is in R plus. Sorry, just R. It's just some real numbers. What this is basically meaning is that if I set lambda I, for example, all equal to 0, then the 0 is always going to be the span of kind of every single vector. Now, if we get the entire vector space, so we get every single vector, then we're going to say that it actually spans V. So we say it spans V if the span of these vectors is equal to V. And this is precisely kind of the thing that we're wanting, right? We want a set of vectors that give us the entire vector space. And if this happens, then we call it a basis. But we need to add one additional condition because, like, obviously, I could take the span of every vector, and then I'm going to have the vector space. So, like, that doesn't really help. So I'd like to minimize this. So in other words, I want to take a set of linearly independent vectors. And this is what we call a basis. So a basis is a set. So we have a set of vectors e1 to en here. If we need two conditions. One is if they span V. And two, so the second condition we need, they are linearly independent. So with these two conditions, we say that we have a basis. Now here it's a set, so it doesn't really matter what the order of these elements are. We just have a set. Now, sometimes later on, it's going to be more beneficial if we give an order to these basis elements. So we will say it's an ordered basis if we have a tuple of vectors. In other words, we're making a distinct order on these. So here we'll have an ordered basis if they form a vector as a base. So here you'll notice some notational differences. If I have a set, notice how it's in curly brackets. And if I have an ordered basis, they're in parentheses. So the notation matters because it's telling us information on what these things are. So let's look at an example of this. An example of a basis. And here we're going to take a fairly small vector space. So here our vector space is going to be R2. And here I'm going to give you two different vectors. I'm going to say E1 is the column vector 1, 1, and E2 is the column vector 0, 2. And I've told you I want you to show me that it's a basis. Okay, so we have to show two things, right? So the first thing I want to show, I'll actually do this backwards. I'll actually show linearly independence first. So 2, linear independence. So how do we show linear independence? So remember what we have to do is we take a linear combination, we set it to 0, and then we show that the scalar multiples have to all be 0. So what we do is we take lambda 1 of E1 plus lambda 2 of E2, and we set this equal to 0, 0. All right. So what is this calculation? What are lambda 1, lambda 2? So let's calculate this out. So lambda 1 E1 plus lambda 2 E2. This is just, so remember how the multiplication worked. I just take the scalar and I multiply it to all the entries. So here we have lambda 1 times 1 times 1 plus lambda 2 times 0 and 2. So here we end up getting lambda 1 plus 0, 2 lambda 2. And then remember to add these, we just smush them together and we do a component-wise addition. So we end up with lambda 1 and then lambda 1 plus 2 lambda 2. So when is this a basis? So this is a basis precisely if, so this, remember we set to 0, right? 0, 0. Now this top row here, this, I guess we'll do this on another page. This implies that lambda 1 is equal to 0, right? They have to be the same. They can't be different. And then the second line, so let's use a different color. The second line here, which we'll do here, this we get lambda 1 plus 2 lambda 2 is equal to 0. Lambda 1 we know is equal to 0. So 0 plus 2 lambda 2 is equal to 0. And therefore we get that lambda 2 is equal to 0. So we're forced to show, so we have that they're linearly independent. Therefore, linearly independent. And you can't see because of my face. There we go. All right, cool. We still have to show a second thing. We have to show span. Span V. So here, what we have to show is that any vector is a linear combination of the vectors I gave. So let's again, so we already kind of have, so what we have to show is that for all, there's lambda 1 and lambda 2, such that we get some vector, right? So this is an arbitrary vector in our vector space. Okay, so how do we show this? We kind of do the same thing that we did in the previous case. So we'll start off with our definition. So here we have the same thing here on the right-hand side. So this here is equal to lambda 1 plus 2 lambda 2. And here we want to have this equal to x and y. So what is lambda 1 and lambda 2? So in this case, we have a very similar thing. So here we have that lambda 1 has to equal to x. And just like before, we have x plus 2 lambda 2 is equal to y, which implies that lambda 2 is equal to y minus x, and then I divide by 2. So with these coordinates, I'm able to find lambdas that give everything nicely, and we're happy. And here, therefore, E1, so I guess here we'll have just a basis. So E1, E2 is a basis of V. So that's nice. But here, one thing to note is that, so here we have a basis, and there's two different ways we can actually have an ordered basis of this, right? So there's two different ordered bases. And here I think it's in the next tuple. Yeah, it's in the next conversation. And basically what we're talking about here is that in this sense, the ordered tuple E1, E2 and E2, E1 are not the same. So even though they span the same vector space and they're both linearly independent and they're the same set, right? So E1, E2 and E2, E1 are the same set, right? So these are the same, whereas these are not the same. I'll emphasize the not. And that's because we care about the order. So here you kind of have to think that the order does give you some extra information. And we'll see about this later on, why this is the case. So why do we care about these bases? Actually, this video is long enough. So we'll stop here and we'll see next time why this is kind of nice, why bases are nice, and we'll talk about the dimension as well. So I will see you next time for that. Peace.